I'm going to start with one of two exercises that we have available to us. Okay, both of these are on Blackboard. I'm going to start with this particular one. Involves cardiovascular disease in New York City, and these are real numbers. These are from the vital statistics that are available on the New York City Department of Health website. I think they're from the early 2000s, like 2004 or 2006 or something like that. So I'm going to take a quick look at these. Now, I separated these out. This data is summarized from a number of statistics that are available in that report for the entire year. I separated out the two populations, male and female, according to the cause of death, cardiovascular disease. That covers a lot of territory, so this may not be a great way to study this particular issue. Might want to be a little bit more specific for a more specific cause of death, but it'll give us an idea of what's going on with this stuff. Okay, now, normally you would expect that cardiovascular disease to be a bigger problem in the male population than in the female population. At least that's what we're kind of taught to accept from the media, right? So let's take a look if that's really true. In this particular year, there was a female population of about 2.8 million females. Notice that that only includes women from or both populations from 25 on up. Okay, so this is not going to come out to the whole population of New York City. Of those 2,800,000 people, there were 12,627 deaths from cardiovascular disease. Now, the rate at which females were dying from cardiovascular disease is equal to the number of deaths divided by the total population. Okay, now rate, anytime you hear the word rate when we talk about biostatistics, you're really talking about a ratio. Okay, so for instance, a rate is how much of one thing happens over how much of something else is going on. A rate could be many things. For instance, speed is a rate. Rate of speed is the number of miles covered per unit time, miles per hour, for instance. The prevalence of a disease in a population is a rate. In other words, let's say we have a population of a million people, and 100,000 of that million people has diabetes, then the rate would be of diabetes, or the prevalence of diabetes in that population would be 100,000 per million, or in other words, 10% of the population, or 10 out of 100, or 100 out of 1,000, 10% of the population. That would be the rate of diabetes in that particular population. In statistics, we call that the prevalence. Okay, so really what we have here is a rate, okay, or a prevalence, either way, of cardiovascular mortality in females in New York City. Now, that's a pretty cumbersome number to work with, right? That's like 0.004 of the female population. In other words, about half of 1% of the female population died from cardiovascular disease during that year in New York City. A little bit better way of describing that might be, instead of looking at it as a proportion, 0.004, let's change it into a percent. And how do we change something like 10% into a percentage? We multiply it by 100. So I'm going to take this value and I'm going to multiply it by 100. I'm just going to multiply the top of the fraction. Same thing as multiplying the whole fraction by 100. Okay, so now we know that there was half a death per, or half a percent, 0.44% per, was the rate of female mortality, cardiovascular disease mortality. Well, even that's kind of a cumbersome number. So instead of doing it per 100 females and having half of a female that died per every 100, I'm going to change that number. I'm going to make it a much bigger number. I'm going to call it 100,000. Now my rate is a little bit easier to understand and to work with. The rate of cardiovascular disease in this population, this female population, was 444 deaths per 100,000 female population per 100,000. Okay, so that's going to be a lot easier for us to understand what that number represents in a large population. I'm going to do the same thing for the male cardiovascular disease rate. There were 9,960 deaths, fewer deaths, although we're going to find that it's a smaller population also. And I'm going to multiply that by 100,000. So I'm going to jump past that step. The rate among males for cardiovascular disease is 413. Okay, so what does this appear to be telling us? It appears to be telling us that females die at a higher rate from cardiovascular disease than males do. That's really contrary to our understanding of cardiovascular disease in females and males. Really, it doesn't make any sense to us. Why would this be? We're going to take a look at why this might have occurred. Okay, and in order to do that, we're going to take a look at, we're going to break down by different age groups the specific death rate within each age group for males and females. Okay, now as it happens, this 12,000 females breaks down this way. 146 of them were in the age range of 25 to 44, 1,000 were in the age range of 45 to 64, and so on and so forth. 6,300 of them were in the age range of 85 plus. Not that surprising because there's a much higher rate of death in elderly from cardiovascular disease than it is from middle-aged or younger people. Okay, so I'm going to actually calculate the age-specific death rate for all these females, and that's going to be equal to 146 divided out of the entire population, and that's the rate at which females die, proportion of females died during that year in that population. Well, now I'm going to say to myself, okay, I'm going to copy this down. Okay, I'm going to say fill down, and it's going to calculate the age-specific death rates from cardiovascular disease for each of these groups. Well, look at this, the highest, look how much higher that oldest age group is. Okay, in fact, you guys know that if I add these all, well, I'm not going to worry about that right now. Now I'm going to do the same thing for males. The age-specific death rate for males in the youngest age group is going to be 277 divided by 1,200,000. Going to be that rate, a little bit higher rate, but basically very similar. Very low rate in either case. And I'm going to copy that down. Okay, and actually, if we look in the oldest age groups, right, these other age groups, it doesn't look that much different for males and females. Yet, it looks like females die at a higher rate. Well, let's take a closer look at this now. Okay, now I'm going to say to myself, why would I get a result that would suggest that females die at a higher rate than males do, when it really looks like males maybe even die at a slightly higher rate than females? This is a bigger number than this is. This is a bigger number than this is, this rate. This rate is a bigger number than that rate is. Why would it look like? Why would we get this 442 versus 413, a higher rate for male mortality? Either one of you guys want to kick in there and let us know why you think that might be occurring? What's the differences in these populations, do you think, that would make that occur, make it appear that females are at a higher cardiovascular disease rate? You can type in there. You can be bold. I don't think it actually, I think the chat box doesn't record when I record the videos. So you can be especially bold. Okay, you'll leave it up to me. Okay, so what's occurring here is that there is a difference in the distribution of these two populations. Females tend to live longer. So the female population that's over 85, for instance, the most susceptible population, is much larger than the male population is. There's a difference in the age distribution of these two populations. And that difference in the age distribution is confounding our understanding of what the real cardiovascular disease rates are in these two populations. Okay, so what I'm going to do now is I'm going to do something interesting. I'm going to reduce this a little bit so I can see the whole page, and I'll blow it up again. Okay, actually, I didn't need to do it quite that much. Maybe about that much. Okay, I'm gonna go over here, and I'm going to say to myself, okay, let's see if I can find what the percentage of males and females are in this population. And since they're in this, I'm going to change this so we stay in the same direction here. Female and male. Okay, so I'm going to say to myself, okay, what's the percentage of females in this particular age group, 25 to 44? Well, the percentage is equal to, it's equal to the population in that age group divided by the total population of females. Okay, now I'm going to put a dollar sign in front of that B and a dollar sign in front of that 20, so that when I go ahead and do this again for each one of the columns below, each one of the rows below it, it's not going to copy this whole thing. It's not going to move the dividend, the bottom part of this. It's not going to move it down as I copy the calculations down. I'm also going to go in here and multiply it by 100 to turn it into a percentage. Okay, times 100. So I wind up in that age group is 47% of the population of females. I'm going to copy this down. Okay, and I can see what the different populations, of course, they all add up to 100%, because that's 100% of the population in that age group. I'm going to do the same thing for the male population. Equals, okay, it's going to be 277 divided by, times 100, to turn it into percent, divided by the total population in that group. And again, oops, I think I made a mistake here somewhere. That should be E. I think that should be E, right? Okay, and then I'm going to put a dollar sign in front of this and a dollar sign in front of this. Hit enter, so that when I go to copy this down, it'll always be dividing by the total population. It won't move that number. Well, let's take a look at this. It's interesting that in the age group over 65, so 65 to 84, there are many more females, a higher percentage, almost 70% of the population of females is in that age group, and only 13% of the population of males in that age group. It's even more dramatic over 85. And these are the two groups that have the highest rates of cardiovascular disease. Over 85, there are twice as many females in that age group as there are males. Twice as large a percentage of the population of females is in that age group than the comparable male group. Okay, so we can see that females are the female distribution of population is weighted towards an older population. And since we're looking at a disease that affects older people more than younger people, it's affecting our understanding of the rate of cardiovascular disease in those two populations. I'm going to make this a little bit clearer by highlighting this. I'm going to go over to charts. I'm going to pick column charts. And I'm going to generate a chart out of this that compares the two populations. Well, let's see what we got here. Whoops, didn't mean to do that. How about if I undo that? Yeah. Okay, let's see if I can do this. Okay, now we wound up with this very nice chart. The blue is female. These are the age groups, and the red is male, and the vertical axis is the percentage of that population, which is in that age group. And we can see that there's more younger people. This group is very low rates of cardiovascular disease. 45 to 64, low rates of cardiovascular disease. As we get into the populations that have high rate of cardiovascular disease, we can see that it affects more the surviving females than the surviving male population, because it's a larger population. And here we can see over here at the extreme end, 85 plus, which has a very high rate of cardiovascular disease. There's twice as large a percentage of females in that group than there are males. So we can see that the distribution of these by age of these populations are different. By the way, by structuring our data in this manner, putting this table together in this manner, I was able to produce a useful graph very quickly in Excel. As we go on in the semester, I'll be giving you some more pointers and help on how you might be able to do that. Many of you guys, this is old hat and you've done this before, but for those of you that haven't worked with Excel very much, we'll be learning a bit more about how to do this kind of stuff usefully. And in fact, SPSS has many graphics capabilities, so that might even be more useful to us. Okay, let me just check to make sure that I don't have any questions. Any questions so far? You guys okay with this so far? We can see that there's a difference in the distribution of the population. Okay, how about somebody just types in there and says hi or so? Okay, good. I need a little bit of feedback every once in a while. Make sure this is still broadcasting properly, if nothing else. Okay, good. So now I'm going to go back and take another look at this. So this time I am not going to look at two separate populations. I'm going to look at the rates of disease in the age-specific groups. Okay, the age-specific death rates from cardiovascular disease for these two populations. But instead of applying those rates to different populations, one population distribution for females and a different population distribution for males, I'm going to apply it to a single population. So we're playing on an even field. Okay, so, and what am I going to use as a single population? Well, one thing I might use as a single population is just to choose either the population of females or the population of males and apply both death rates to each of those individual populations, each of those to that same population. So we have an even playing field. In this case, I decided, well, instead of doing that, you know what I'm going to do? I'm going to add these two populations together, and this represents the total population in New York City in those age ranges, rather than split up into male and females. And I'm going to apply those age-specific death rates for females and the age-specific death rates for males to the same population distribution, and see how the cardiovascular disease rate looks then. Okay, so now you may notice it comes out to 5.2 million. That's because we were excluding a lot of people because it only goes down to 25. Okay, so New York City's population probably more like 8 or 8.5 million at this stage. Back in these days, even then, probably pretty close to 8 million. Okay, so I'm going to copy these age-specific death rates for females. I'm going to go up here to Edit and Copy, and I'm going to go down here and highlight the same set of boxes, and I'm going to say Paste Special, and I'm going to tell it to just paste the values, the numbers, because I don't want to worry about transposing these cells and stuff like that, because this is a calculation. I don't want to confuse the calculation. I'm going to copy the age-specific death rates for males and put them in there. And again, I'm going to say Edit, Paste Special, and I'm going to say just copy those values. Now, if you're using a PC, you'll see that you can get to fill down or copy down and so on and so forth. You can get to it from the edit menu as well, but you can also get to it. There's usually a little drop box over here somewhere in this area of the what they call a ribbon in Excel. It's usually on the home ribbon, and for instance here on the Mac, it's over here in this end. And fill and fill down and so on and so forth at this end. On the PC version, it's probably going to be on this end somewhere. Okay, so you can use that instead. But I like to go up here. It's just habit with me. Okay, so at any rate, these are the age-specific death rates. Well, now what I'm going to do is I'm going to say to myself, if women are dying at this rate in this age range for this population, how many deaths among females would I expect? I'm going to calculate the number of deaths I would get. So it's going to be 2.6 million times 0.000 and so on and so forth. And it comes out to, I would expect 283 deaths in this population if females in this larger population were dying at that rate. I'm going to copy this down and calculate the deaths in each one of these populations at those different rates. Notice this little small population of 121,000, the oldest women. Let's see what happens when I copy that down. I'm going to go over here and say fill down. Okay. Look at that. I have 8,000 people. Almost the highest number of deaths is occurring in that group, even though it represents a very, very small portion of the population. Okay, so the total number of deaths that I would expect among females if they're dying at this rate is going to be equal to the sum of all these different groups. Okay, I would expect 19,552 deaths. Okay, well, what would I expect? So what does that tell me that the mortality rate is for females in this population? Well, as before, it's going to be equal to the number of deaths divided by the total population. Okay, and then now I'm going to take this, I'm going to put it into parentheses this time. And I'm going to take that number and I'm going to multiply it by 100,000. Okay, so that I'll get a death rate, instead of a fraction, a proportion, I'll get a death rate per 100,000. So women in this population dying at this rate, if the true population of women were this distribution, they would be dying at the rate of 371 women per 100,000 population. Well, now let's do the same thing with males. Equals this proportion times the same population this time for females and males. Whoops, made a mistake there. It's this proportion times this population. Oops, what did I do there? Oh, I divided. I meant to multiply. Equals this proportion times this population. So we would expect 571 deaths for males. Now, another way I can copy this down is just to focus on that corner and drag down, and it'll copy it down for me as well. Okay, let's get the total number of deaths that I would expect if people in this population were dying at the rate that the males die within each one of their age groups. So the number of deaths I would expect now is going to be 26,916. So I'm going to calculate my mortality rate for males, and mortality rate for males is going to be my expected number of deaths divided by the total population, right? Put parentheses around that and multiply it by 100,000. I could also just multiply the top part of the equation by 100,000. Whoops, I made a mistake again. Equals those number of deaths divided by the total population, and I'm going to multiply by 100,000 again. Times, I think I left out the asterisk probably, is what I probably did. Okay, and I wind up with 571 deaths per 100,000. So when we applied these death rates to two different populations, it appeared, in fact, that cardiovascular disease for females were higher than males, when in fact, the cardiovascular disease rates for males are quite a bit higher. It appeared the opposite because of the difference in the distribution of the populations for males and females. There are many more older females surviving into these older age groups which have very high cardiovascular disease rates versus the number of males that survive into those age groups. So we have managed to adjust for the difference in these populations, and this would be termed our age-adjusted female mortality rate and our age-adjusted male mortality rate. This process is something called standardization. In other words, we can standardize on a single population so we can see the real difference in disease rates between the two of these. Okay, and this might become a useful tool if we have differences in population based on ethnicity, based on the amount of alcohol consumption, and so on and so forth. And we want to remove those confounding factors so we can compare the two groups by basing them on populations that have similar parameters in terms of these other values. So standardization, in this case, standardization based on age, or in other words, age adjustment, is a valuable tool to allow us to understand, what the or tune out the effect of differences in the distributions and populations of other variables like age. Okay, so how does that sound? Does that sound okay to you guys? Make sense? Thanks for by the way, Gabriel, thanks for the hint. Okay, I did get the wrong box. Did I get the wrong box in there? I think, yeah. Okay, how do you feel about that? You guys okay with that? I'm going to save this. Oops, wrong box. Save as. Save as, and let's see if I can't find a good place to save this. I'm going to put underscore solution. Okay, so I'm going to post both of these. Yeah, I'm going to post this to Blackboard. In fact, before we split, I'm just going to take another minute. I'm also going to put up another file, which Professor Weicker uses most of the time in her class when she's teaching this during lecture. In this version of this, okay, I'm going to make this smaller so we can see the whole thing. In this version, we have a discussion of the idea of rates and how rates are determined and what rates mean. And then we have a situation where we're looking at the, by the way, a lot of times if you don't age adjust, you'll call it, rather than call it just mortality rate, you'll call it the crude mortality rate. In other words, unadjusted. Okay. In this case, we're looking at the mortality among females in Alaska and in Florida. Well, in Alaska, there are about 300,000 females, much smaller population. In Florida, there are 6,700,000 females, large population. But, we expect what we wind up with when we look at this. Let's take a look at the number of deaths in Alaska. Out of those 300,000 people, we have 1,400 deaths. In Florida, out of those 6 million females, we have many more. In other words, 73,000 deaths. Well, if we did, now this mortality rate due to cancer. Before we were looking at cardiovascular disease, now we're looking at the mortality rate due to cancer. Even though there's a difference in the two populations, the size of the two populations, the rates of cancer, unless there's some exposure or some other issue that we don't know about, we would expect the rates of the crude mortality rates for deaths due to cancer, even though it's different population size, we'd expect the rates to be the same. We'd expect women in Alaska to be dying of cancer at the same rate as women in Florida. Let's just do that one calculation right now. So that's going to be equal to the number of deaths in Alaska among women from cancer over the total population of women in Alaska. And I'm going to multiply that by 100,000 as we did before. So per 100,000, we have 476 deaths per 100,000 among women in Alaska, all age groups. Okay, well, how about in Florida? Well, that's going to be equal to the number of deaths, total number of deaths in Florida, divided by the population of females in Florida. Okay, and again, I'm going to multiply that by 100,000, parentheses, times 100,000. And I'm going to, well, look at this. We have more than double the rate of cancer mortality among females in Florida that we have in Alaska. Well, what is that? Is there some exposure in Florida that's not present in Alaska? Is there some toxins, some pesticides, some cause that we don't see that would make females die at a much higher rate in Florida than in Alaska? Well, with these tables, you can now calculate, as we did before, the mortality rates, age-adjusted, the age-specific mortality rates for all these different age groups of females in Alaska, and the age-specific mortality rates for females in Florida. And once you have that, you can say, well, let's apply this to a single population rather than two populations. Perhaps there's a difference in the distribution. And you can copy down your death rates, your death rates, your age-specific death rates for Florida and for Alaska, and you can calculate the number of deaths you would expect, and then calculate your age-adjusted mortality rates. And I think that you probably can guess that the population age distribution for Florida is much older population than the population in Alaska, including for women, probably men too, I would imagine, right? Because it's a popular retirement spot. So perhaps this is due to age. And the way you're going to tease age out of this so you can get a closer look at it is you're going to adjust this mortality rate for age by applying the rates, the individual rates, age-specific rates, to the same population. We could have chosen the population of Alaska. We chose the population of Florida as our standard population. You could have also added two together. You could have used the population of the United States. You can make basically an argument for many different populations that you could use as a standard population, but it's often convenient to use population for the population distribution for one of the two populations you're looking at, because you already have that data. If we were talking about the boroughs in New York City and you were comparing Queens to Brooklyn, you might use the population of the city as a whole as a standard population to compare the two rates. So I'm going to leave it up to you guys to do this calculation and find the answers. And you'll find on Blackboard also a copy of the answer sheet for this as well.